Hey everyone, how are we doing? It is Mega Mondays. Let's put some mega points in the chat. I see, can we do some practice questions? I cut my, I got a band-aid on my neck. I tell you, just, it's never, I don't know. I'm just going to cut myself every time. That's what happens. That's life. I'm just figuring someone's going to notice. Anyways, life. Anyways, how's everyone doing this morning? Hey, what's up, Jonathan? Hey, Tori. Hey, Ella. Hey, Cooper. Hey, Grace. Good to see you, everyone. We got two Graces here today. And so we got some practice problems. My background's breaking as usual, but everyone is here. Let's see. We've got, what questions? Can we go over the campaign question on the Canvas content quiz? Let's do a vote. I'm doing good this morning. I'm on second cup of coffee, almost done with it though. So maybe third cup, I don't know, or some awake chocolate, just tons of stuff. Can we go over the Canvas content? Yeah, let's do the Canvas content quiz first. Let's do that. Because that is something big right there. I'm going to pause the video of myself. Let me get the Canvas content quiz up and going. What should we do next after the Canvas content quiz? Let's talk over the Canvas content quiz. I'm going to look at the Canvas content quiz. I'm going to talk about some questions on it. So get ready for some really good advice. Okay, let me go get the Canvas content quiz. Canvas content quiz number. Today is the 29th. This is the 7th Canvas content quiz. So many Canvas content quizzes. Let's go over here to the preview button. Let's talk over a few versions of it. What is the sample space? Okay, yeah, this one's good right here. Let's go and take a look at it. Let me get the chat up. And then we got feeling good about the exam, just scared now for how things might be worded. Yeah, you got it. Don't worry, you got this. I got my answer. I want to make sure I'm right before I submit. Possible some true false. You bet. Let's do that. Let's hop to the main screen here. We should be going to the main screen now. We're on the main screen and we're going to pull up some Canvas content quiz. I feel like I really want to have as much study time as possible. Oh, that's all right, Coop. No, ask some questions. You got it. We're all here to help out. We're all here to learn. Let's see. Let's do this one right here. I think this is someone wanted a true false question right here. This is a really great question right here. Let's take a look. What does everyone think about this? And let's review the concepts behind this and make sure we understand why this is true or false. So here's the first Canvas content quiz example question. We'll do a few example questions so you can see some questions that may be on there. Oh yeah, Tori, we can do that. You bet. So what do people think? The three conditions of sampling distributions must be met in order to calculate p hat. What do people think right here? Is this true or false? What would you put right here? To calculate p hat, we must meet the three conditions. To calculate p hat. And what is p hat? This is good right here. So we need to first know what is p hat. And we're talking about the sampling distribution of the sample proportion, which if it is everything met, it's going to look like this. So this should be false. Do not worry. Let's throw yes, because what is p hat and how do we calculate p hat? So this is false. Let's throw some points. Thank you, Jonathan. Do not worry if you get it wrong. This is our chance to practice. And what is p hat and how would we calculate p hat? Like what is p hat? So the first thing we should think of is what is p hat? P hat is this. And what is p hat? P hat is the number of successes over the number of trials. And that can always just be mathematically calculated. Does that make sense to everybody right there? That is like, so like write an example question in the chat right now to see if you know what p hat is. Great job, Grace, right there. So like, how would we write this? How would we write this as a question where we calculate p hat? I'm gonna triple check my answer. I always have this fear. Let's see, am I going to get a 20% on this quiz? Why do I doubt myself? Yes, I am correct. I got a 20. Awesome work. I have this fear that I'll tell everyone a wrong answer, and everyone will be like, Brian, you said this in the video and it's wrong. I'll be like, no. So right there we have n equals 200 and like x equals 50. And so when you think about this, it would be something like this. We go out and talk to 200 people, and that's going to be n right here. And then from those 200 people, what? 50 of them say that they own a dog. That 50 that own a dog would be X. And what would be the sample proportion there? So think about this. What does sample proportion mean? Like put it in words like what a sample proportion means. To say from a sample of 200, 50 people said they own a dog. So you have right here that you ask people, do they own a dog? and 50 of them say they do own a dog out of the 200. And just think about what a sample proportion means. Exactly. And that, like, that's a success. Like 50 of them answered in the affirmative way, like the way we're checking for, like, do you own a dog? And 50 of them say yes. So now we can get the sample proportion of people who own a dog. And how do you know it's a sample proportion? It always has a sample size. Yeah, Grayson, let's mention that. So when you have and I always go from this order, we'll mention this right here briefly, and I'll do that one next, Grace, you got it. So what do we get by meeting the three conditions? By meeting the three conditions, what do we have here? What do we have by meeting the three conditions? By meeting the three conditions, what will be true? And I'll give you a hint. This. That is what we have. It's not going to be p hat. P hat can always be calculated, so we'll put p hat in green here. That's this topic over here. P hat can just be calculated mathematically. Exactly, Campbell. We have the normal curve. By meeting the three conditions, we have the normal curve. So by meeting all three conditions, the central limit theorem implies that the distribution will be more normal and it'll be tighter as the sample size increases. Those are the two factors to the central limit theorem. We'll do a few more. We'll mention Grace's question right here. And thank you so much. Keep asking the questions. I'm going to try to get as many in and talk about these. So a way to remember population, and then we're going down sample frame, and then sample. So I always do them in this order every time, and this goes down in order from size. So let's get some definitions. This is time to practice right here. Make sure you have these on a note card or you are be able to type them out. What is a population? So what is a population? So just define right now for a population for me. Define a population into existence. If I say we want to examine a population, let's do that, Grace. We'll do the probability one. You got it. What is a population? What is a population? Population is everything we want to understand exactly. Like maybe we want to understand students at UTK. So we've got UTK students. So maybe UTK students. So we're saying, let's go and try to understand UTK students. So this is every person or thing we want to understand. Now, what is a sample frame? Like you always want definitions here. What is a sample frame? So the sample frame, when you think about the population, you've got a whole bunch of students around here, around campus. And then you'll have a sample frame. And the sample frame is going to kind of look like a frame because it's going to be what? What is the sample frame right here? The sample frame is going to be, did you find out if we were supposed to use our no student ID? Yep, no student ID, Kayla. Great question, Kayla. No student ID. We're all using the full sample for this one. About starting another class and homework, I have a question about number 8. Do we need to use the pairs command for task 1? The 2 seconds, everybody on. Oh, shoot. Let me get that assignment here in a second. I'm trying to think. No, you should use the pairs command for task 2. Wait a minute. Which part of task 1? I think there might be there's a pairs command somewhere in there that really works well for looking at the unusual nature with the influence plot. So it might be students at the library, the individuals we have access to. So maybe it could be Pres Court students. So if you go to Pres Walk student, Pres Walk. So maybe we go out to Pres Walk. Does that make sense to everybody? If we go out to Pres Walk, just the presidential walk, and we talk to students there, those are the students who are on presidential walk at that time. Does that make sense? Like the presidential walk, like if we go and talk to students on presidential walk, students on presidential walk are the students we have access to. Does this make sense here, Grace, that the sample frame are the students we have access to speak to? So we could talk to any student who's on Pres Walk. Now, not saying we will talk to them, it's just students we could theoretically speak to. So now we get to the sample, students we sample. Let me look at 320 here in 2 seconds so I answer that question right there and make sure we have it. We'll use the full date. Yep. And then the students we actually talk to are going to be our sample. So when you go down from population, we want to understand all UT students. Population is every person or thing we want to understand. And then it could be convenience bias. Yeah. Going to Pres Walk might just be students who are easiest to talk to. Think about students who, especially during the pandemic, are not going outside. Like I don't go outside much. So if we were to ask them questions about the pandemic, like, do you think it's safe to come to campus or questions like that? I mean, if you're on campus asking that question, you're going to have a big bias asking the question. So we have to watch out because how you select your sample needs to be representative. And if you're asking a question that could undercover certain portions of the population due to something like convenience bias, Campbell brings up a good point right there. So going to pres walk might just put in some convenience bias to what we're doing. So great examples right there. Let me go grab the 320 assignment really quick over here. Just take a really quick look. And then Roderick, restate your question. You're asking about the pairs command, I believe. And then we're going to hop back to 201 and do another. But thank you. Please, 320, ask questions. I'm going to try to do as many questions as we can. Do all the questions. Every single question will be done. So please ask all the questions. Do not worry if I'm already taking one question. Please put your question in the chat, and I will try to remember and keep all questions straight. Class is not over. I'm just making sure everything loads up. I will reappear here, and everything is loading in the background. We're going to do another. I think we had a probability question next. Someone was wondering about. Okay, I've got the assignment up. Let me take over the classes over screen. Keep asking those questions. So for task 1, you are, and this is a much shorter assignment, it's only 2 tasks this week. You are make a multiple regression, interpret average temp, create influence plot, identify very unusual rows. Here we go right here. Yep. So right here for this one right here, I would, and I think hopefully we find out my Pearson. It's a little bit weird this morning, Clarissa. Some people have had it work and some people haven't. And I'm hoping it starts working consistently because this is going to be really bad if it's not working today and tomorrow. So I'll keep everyone updated, Clarissa. And if it goes a little bit later, I'll definitely be extending it. And I'm really talk about the day for my Pearson to break, the day before the test. Thank you, my Pearson. Thank you, my Pearson. So I'll keep everyone updated on it. I found out this morning. I'm really sorry about that, everyone. My Pearson, why are you doing this to us, my Pearson? So this right, I know, no, thank you, everyone. I'm just like, and then I think we're gonna do cluster versus stratified next. So right here, Roderick, I think you're talking about this part. The pairs command can totally be used. So Kayla and Roderick, this one is a great one to use pairs, or you could do summary of individual variables and look at the row. So here's my suggestion for this one right here. Yeah, we can do confidence intervals after strata and cluster. So let's do strata cluster and then talk about confidence intervals. You bet. So we're going to do strata versus cluster. So make sure you have your note cards and definitions for these. So stratified is going to be 1, acknowledge a difference. So we acknowledge a difference in the population. And then 2, sample the groups randomly by the percentages. So this is stratified in a nutshell right here. And cluster, we put items are randomly put into groups, select the groups randomly, and last but not least, you should be thinking this right here, perform a census on the group, which means take all the observations in the group. So this is a brief definition of stratified and cluster right here. Strata is finding a difference in the population. Boom, right there. Great job. And so what if I told you, let's go and sample dorms at UT to see if people like dorm life, like to see what they think about, Brown versus Stokely versus Orange and White. And please tell me the names of the dorms again. I'm trying to remember. I don't know. They changed them and I wasn't around and I don't walk by them, so I don't see them and I don't know them. I just saw it in an email. But anyways, if we want to ask people, do they like the dorms? Should we use a cluster or stratified method of sampling? So, and think about what it would mean if we use cluster versus stratified, how we would sample if we're clustering or stratifying on dorms. Because you could cluster sample. Hess and Massey have been around a while. So Hess is going to be across from the library, and Massey's behind Grieve, right? And Grieve's no longer a dorm. So, and what would it mean to stratify? So think about what it means to stratify. And so why would we stratify? And you are correct. You are correct. I'll give you that. You are correct. I would stratify. Because if we're saying cluster, you could cluster sample dorms. I wouldn't do that. It would be a bad way. Reese's Elite. Yeah, Reese, what's the one that's gone now? Isn't Reese next to the Carricks? Is Reese still around? Oh, is it? can't I think of it? Humes is gone. Humes is destroyed. Hey, what's up, Andrew? Good to see you here. And so if we were to cluster sample dorms, you would take random... Morel's gone now? What did it... Wait. Oh, yeah, Morel's gone. That was behind the Carricks. I was thinking of different one. Yeah, it's been gone a while, I think. Man. We'll take down Grieve eventually. My dorm. So if you were to cluster sample dorms, you would be taking like whole dorms. Like you would take like, you know, Clement or something or Hess, and you'd say like, let's talk to every student in that dorm about their dorm life and ask them how it is. But when you think about this, like there's differences between Laurel, which is more in the fort and is more apartment style living from what I know, where, you know, you have like Stokely and Brown and other dorms that have very different structures and everything on campus. So you acknowledge the difference that the dorms are different, and then you would sample students randomly from each of the dorms. You would pick random students by the percentage of the students who live in the dorms. So bigger dorms, you would speak to more students, and smaller dorms, you would speak to less students. Does that make sense what stratifying is? Because I always think about, there's this classic picture, strata in dirt. There's this really great Wikipedia picture, stratum, and let's show it right here, with this person who's appeared on the channel about 1 billion times now, showing different strata. And if you look at the dirt right here in this picture, it's different. There's layers. And so if you were to take samples from this, you would take more of a sample from this area up here, and you would take smaller samples here, like you're going to sample by the percentages. Does this make sense? Message me in the Discord on it. Message Roger and I'll take a look, and we can definitely mention that. Send me which one are you working on? Send it in the Discord which one you're working on, and yeah. So then we will take a look at that. Does this make sense right here that you wouldn't want to take a cluster? Because what would a cluster sample of this look like? If you took a cluster sample of this side of the mountain, you would say that these are randomly put into groups, and you would go to it, and you would go here, and you would say, I'm going to take all of this area right here. I'm going to take all of this portion. And would that be representative? Because you're going to take a cluster, you're going to take a whole bunch at once, and that would not be representative. So now the question becomes, when do we take cluster samples? Well, how are students kind of randomly put into groups? How are students randomly put into groups? So how are students randomly put into group? It's all the same. We would want to like acknowledge the differences between the groups of dirt right there, and then we would sample like percentage-wise, like the small areas and the large areas more. So how are students like randomly, how could you take clusters of students? And you could do a cluster stratified with the dorms. So I'll mention that here in a moment. And then you might say, well, it's not always random what this you're on. How could we cluster sample students? Like what ways? Well, grade levels sounds like a difference. So if we have different grade levels, those are like differences among students, because then you'd be taking all of one grade level and you'd be like, it's a little too not so randomly put into grade level. Does that make sense, Campbell? So that would be more like stratifying. If you're doing grade level, you wouldn't want to take all freshmen, all sophomores, all juniors, because if you were to take, now major also though, major is going to be a difference between students, because if you were to cluster sample on that, you would take all psychology majors, and that wouldn't be representative. Does this make sense right here? Clubs are probably a difference too. So clubs are probably going to be stratification, because like if you're in like, let's say like a political science club or things like that, there'll be differences. Great answers, everybody. Keep the answers coming in. What way do you think we might be able to cluster sample students? And it's a really hard one to figure out. Like this one's a lot harder because sometimes students aren't randomly put into groups. What if we were to go to classrooms would probably work. Like now you're not saying like what kind of classroom, you're just saying let's go to random classrooms. Like imagine we have a list of all classes that are happening right now at UT, like in-person classes, and we go to like 5 random classrooms. Now you might be saying classrooms have differences, but let's say we pick like gen eds, but then they're for younger, or not younger students, but more like freshman intro classes. How about we do this? We go to the cafeteria and we talk to tables of students. So we go to the cafeteria, and you might say you're more likely to get on-campus students. Okay, no sampling method is perfect. But we go to the cafeteria and we just talk to tables of students. And each table of students is like a group we're sampling at one time. Does that make sense what a cluster is? Like you hopefully have them randomly put into groups. And it's hard to achieve that sometimes, but we're just going to go to tables of students in the cafeteria, and each table of students is going to be a cluster. Like you're just taking a whole bunch at once. And how many of those students are we going to talk to at that table? Right down here. So you can type a short word. How many of those students are we going to talk to at that table? So when you take a cluster, they should be randomly put into groups. You're going to select those tables randomly. So we have random people put into groups, and then you go to a random table, and then you talk to how many people at that table. So the cluster is about like, we're just taking a whole bunch at once, but you don't want to have differences. So how many students are we going to talk to at that table? Because it's an important keyword, all of them, right? Yep. So the hard part right here is cluster is always just about taking a bunch at one time. Like clustering just speeds up the process. That's like the point of clustering, is just to make the process a lot faster, where stratification is about fighting under coverage bias. So let's put that note right here. So an important note to kind of help maybe understand why we use these is helps fight under coverage bias. So this is going to help fight under coverage bias, which is not a word, or it is a word if we do that. And sure, why not? And this one is going to speed up. So it's just going to speed it up right here, where this one's going to fight under coverage bias, because we're going to make sure we get the right amounts of everything. Does this help make sense of it right here? The difference between stratified and cluster, where stratification is like we're acknowledging a difference. We're saying, okay, majors have differences. Like there's a difference between a psych major, a supply chain major, a marketing major. So we're going to sample a certain percentage for each. Yeah, exactly. Undercoverage is going to mean there's either too much or too little. So we're like, okay, we need to make sure we get the right amount of psychology majors, the right amount of supply chain majors. And so we're going to stratify on that. And then we're going to sample a certain percentage of each major. So you're acknowledging a difference. You're saying, we need to make sure we have this many psych majors, this many supply chains, this many marketing, because we don't want to undercover those areas. So what would a cluster be like if we took Carrick and randomly sampled a few people from each floor? Remember, wait, so Cooper, big thing right here. So whenever you see cluster, what must there be? Whenever you see cluster, there's always this element of it at the end. So would this be a cluster of all individuals donating blood at a randomly selected blood drive? I believe so. Yep. That'd be a cluster sample at location, Kayla. Great answer right there. That'd be a cluster sample at location. So it'd be because you're doing it. And so Kayla's got the key element right there of the census, that you have to take information from all individuals. Whenever you go to a cluster, you get information from all individuals. So if for Cooper's example, if you went to Carrick and then you randomly selected a few people from each floor, you might be doing, if you acknowledge the difference between each floors, you'd be stratifying. You'd be stratifying by each floor. So if you're saying there's differences in the floors, which some dorms have like honors floors and engineering floors, so you would be stratifying by floor. Then if you went to a dorm and you're saying you want to understand Carrick, which that would be representative of Carrick, and then you said, I'm going to sample percentages of each floor, then you'd be stratifying by floor by saying the floors are the differences. Now, whenever you cluster sample, the big thing we should notice, and let's highlight this right here. The census idea is really huge. Whenever you see that, that's a giveaway. It's cluster. When you see like they talk to all the individuals, then it's a cluster. So what would it mean if we cluster sampled by grade level of freshman, sophomore, junior, senior, and why would this not be representative? We have freshman, sophomore, junior, senior. If we treat these like clusters, what would we be doing, and why would that not be representative? Freshman, sophomore, junior, senior. If we treat this like clusters, and then we say, let's cluster by grade level, why would that not be representative? And remember the key word right there. So why would doing a cluster sample by grade level not be representative? And then we'll do another Canvas content quiz, and I think someone had another one after this. Why would cluster sample by grade level not be representative? And then Conference will do next. You would be sampling all of one grade level. You'd be sampling all of one grade level. Does that make sense? So you'd be saying like, let's go to freshman, sophomore, junior, senior, and you'd have these 4 groups. And in these 4 groups right here, you would say, let's sample all sophomores. Let's like go and sample all sophomores. And that would not be representative. So what you want to do is, obviously they're going to be like different sizes. So you would go here and you'd say we have more freshmen, we have more, maybe they go something like that. And you would sample a percentage of each of these based on how large they are. So you're acknowledging a difference and you're saying we're going to stratify by grade level. So this would be stratifying by grade level would be representative, but cluster would not. I just got out of class. Could you describe how to find the margin of error? Yeah. Let's do margin of error stuff, which might be in the Canvas content. Let's see if there's a Canvas content quiz question that goes over margin of error. And because another person was asking about confidence intervals. So let's see if we can combine two questions into one. Describe the sample size. Decreasing the sample size will make a smaller margin of error. Okay, cool. We got another true-false Canvas content quiz question. And let's go grab it right here. And let's figure it out. Okay. So here's another Canvas content quiz question. It's with confidence intervals. And it's dealing with the margin of error. It was your number 5. Was it this one right here? So decreasing the sample size will make the margin of error a smaller value. Okay, let's write out our confidence interval formula and make sure we understand it. So we have here p hat plus or minus z, and we put a star, means you get to pick it. P hat q hat over n square root. So let's review. P hat is the what? P hat is the what? What is p hat right here? Oh, we can do that one next. You got it, Caroline. We'll do that one next here because lots of good conventional questions. And then I think I can kind of put that question into this one too. So what is p hat? Well, we are interested in the population parameter. P hat is going to be the sample proportion, and we are interested in understanding p. So p hat is going to give us insight into p. So p hat is the sample proportion, which is our estimate of the truth for the population. So it is connected to the population parameter, but we would say I went out and spoke to 50, 100, 200 people, and 50 of them said they own dogs. So my estimate of the true proportion of people that own dogs is equal to 25%. Now the z-score is part of the margin of error, and the z-score gives us our what in the interval. Like the z-score right here is directly related to your what level. The z-score is going to be directly related to the what level. So let's draw this right here in the corner, which will go out here. The z-score is directly related to the what level of this interval. So the z-score is going to tell us our percent confidence. Nice job, Ella, right there. It's going to tell us our percent confidence. And 1.96 is the classic z-score for a 95% confidence interval. That's the very exact one. So how much of the area we shade, if we make it wider and wider and wider, we get more and more confident. And then last but not least, we need to know how to find Q hat. Who can find Q hat for me in the chat right now? Who can find Q hat for me? So try to find Q hat for me. Go ahead here and try to find Q hat. So can you find Q hat for Brian? What is Q hat in Brian's equation? Take a moment right here. What is Q hat? Great job right there, Samson and Carson. Excellent work. What is Q hat right here? So see if you can find it in my equation. You got it. You got it. Everyone knows how to do that. Yep. Q hat and P hat are complements. So always remember Q hat and P hat are just the complement of each other. Really, really quick solve right there for Q hat and P hat. And now I want to point something out. So decreasing the sample size will make the margin of error a smaller value. So if you were to have this number right here on the bottom go towards infinity, if this were to go towards infinity right here, what would happen to the margin of error? So, I can show that here in 2 seconds, Grace, you bet. So, and I'll show exactly how to get that. If you were to have the sample size go towards infinity, just think about like something over infinity. This whole thing right here would go to what? And then we'd be timesing something by this. So the margin of error does what as this right here. So as the sample size increases, and we'll put this over here on the side, I'll put it next to me here. So as the sample size increases, so if sample size increases, margin of error will do what? Camel might have the answer to the interval. So if sample size were to get higher, margin of error gets smaller. So the margin of error is going to go down. As sample size increases, margin of error goes down. So they're inversely related. Decreasing the sample size will make the margin of error a smaller value. This is true or false. This is 100% false. So they're inversely related. Exactly, Cooper. You're seeing it mathematically here. So, and just think about this theoretically for a moment. Like, would you better understand something if you got a larger sample size? You would. If you got a larger sample size, you'd have a better understanding, and your uncertainty would go, not your uncertainty, I should say, but your interval would be tighter. You would have a smaller interval. And so a really great question right here. Grace asks, how did you get 1.96? This is a very famous number in statistics, this 1.96, and I'm bringing up the David M. Lane, 2 seconds, and we'll have David M. Lane on the screen. But aside from memorizing these numbers, which you do not need to do for the test, you do not need to memorize these numbers. And we're going to do, I think it was Caroline's question. You do not need to memorize these numbers. We will give you either pictures on the test, or we will just tell you the answer. We could give you a picture, something like, actually this one could be a picture too, because the middle 95 needs to be shaded. This is a little bit confusing right here. This question could, or this picture could catch people off guard, but this could be used to create a 95% confidence interval, because what is this picture showing you? This picture right here is showing you on the top right, there is 2.5% of area, and I always suggest that people write this out on the test if they can, or just on their sheet of paper. If we were to draw over here, now how much area is shaded in the middle, like, or not shaded? If we have over here another, so what would be in the middle? Yeah, let's do the bust probability. You got it. We're gonna do one more confidence interval, and then we'll do the bust probability. You got it. Thank you so much, everybody. Great office hours today. How much would be right here in the middle? So increasing the sample size. Yep, Campbell, great answer right there. They're inversely related. If you increase the sample size, margin of error gets smaller. Great answers, everybody. So much help out in the chat. Love it. So how much area is shaded in the middle on this graphic right here? So we only originally had, we didn't have all this on it. I drew these in extra. Oh no, we didn't want to do that one. Well, now if I delete it, it's going to go away. So how much area is shaded? 95% exactly. And we could give you a graphic that wouldn't have this. We could show you. That won't go away. Oh yeah, sure. Very little of it'll go away. There we go. We could just show you this right here. So this right here has 2.5% on this side. You're fine, Campbell. And then we could show you the graphics and have you compute it. And so, yes, so double check that. There was another question about, I want to point out some stuff about the margin of error. Let me show you how to solve margin of error questions the following way. I think sometimes we overcomplicate it by trying to memorize formulas, but we all know, you'd be like, Brian, I don't know that. You'd be like, I promise you do know it. Your friend tells you that a new gaming system is coming out, and it's going to be between $400 to $500. Who knows the margin of error for this interval? Your friend says, oh man, the new Nintendo system's coming out, and it's going to be between $400 to $500. You'd say, oh, I know the margin of error for that. Who knows the margin of error for the new gaming system? So this is $50 right there. You just did it instantaneously. Now, Caroline, you got it. You got it. Watch this. You ready? The margin of error is always what of the whole interval? The margin of error is always what of the whole interval? So the margin of error is always what of the whole interval? And then you know you've computed it if you can say plus or minus on it. So you got it, Caroline. Don't worry, we're throwing out some 50 points. No worries, Caroline. This is the practice. You got it. And this is the practice. By being here, Caroline, you just got everyone 50 points. Because you have to practice and you have to be like, oh, wait a minute. It's going to be half the length of the interval. And then you're like, I got that. And that's now test knowledge. So we can write some formulas right here. Let's write a formula. Upper minus lower divided by 2 is equal to the margin of error. And this is the upper and this is the lower. We also have the upper plus the lower divided by 2 equals the center of the interval. And all we're doing right here is just finding the what of the two numbers. By finding the center, all you're doing is just whatting the two numbers in the interval. So by finding the center of the interval, you're just finding the what of the two numbers. By finding the center of the interval, you're just finding the what of the two numbers. So the center of the interval is just the what of the two numbers. The center of the interval. Thank you, Campbell. So much positivity, Campbell. Thank you. By finding the center of the interval, you're just finding the mean, the average, the middle. You're just averaging the numbers. So seeing concepts like this hopefully make more sense. If you're like, it's between $400 to $500, well, then that'd be $450 plus or minus $50. So remember that when you have an interval, if you go here and take half the length of the interval, half the length of the interval is going to be the margin of error. Half the length of the interval is the margin of error. So just practicing this and doing problems like this will hopefully put it in our heads. Do not worry if you make a mistake. This is the time to practice. This is the time to make mistakes. We like wrong answers. We get them out of the way before the test. The more wrong answers we do now, the more we learn. So keep answering questions. Do not worry. There was a question about, what was the one that people wanted? Let me go find it again. I'm going to pull up Canvas Content Quiz 7. We're going to stay over. Do not worry. We're not going to end at 1 or 2. Your time. I tell you, time just flies. Does anyone feel like that? Like, I'll start teaching and I'll just be like, holy mackerel, like we are flying through time. So the question was, I know, Miranda, it's crazy. Do you mind going over the coin example you do? Which coin example, Campbell? Can you go into a little more detail? Can you grab the bus problem from the Canvas content? Let me look at the bus problem. I'm going to grab the bus problem, and Campbell, if you want to, so let me find the bus problem. Where's the bus problem? Where you at, bus problem? Here we go. Found it. We are good. It's literally the first problem in the first bank of questions. So let's grab the bus problem and let's solve the bus problem. Thank you for being here, asking the questions. Keep asking the questions, and we'll try to do as many as we can. That's our goal today. As many questions as we can. Okay, let's do the bus problem here. So, like, how is it Monday? I know. I wake up and I'm like, what day is it? What's going on? Where am I? Who am I? Mine's a 95% confidence interval of the population. What is the margin of error? So what do we need to do? So first thing, Caroline, to answer Caroline's question, let's review. Caroline, you should first find the what of the interval. So Caroline, so here's the formula right here. So you should do what right here? Yeah, Grace, put part of that question in here and we can check that out. My Pearson's hopefully working. So Caroline, what should we do with your interval? We'll finish up this question here. So what should you do to your interval right here? So think about how to solve this one. Who can mathematically solve this one using the equation we have right here? Like take this interval. So a confidence interval for such and such has limits 400 to 500. You got it, Caroline. Yep. You're seeing it. You're seeing it. That's right. That's right. Is it like the better you understand it theoretically, and then you try not to memorize the formula, like, oh, we just take half the length of the interval. So because it's just half the length. Always remember how it looks right here. It's just half the length of the interval. And what is the full length of this interval right here? 100. You take half the length. Great job, Tori, right there. Find the distance, divide by 2. That looks to be the answer right there. Exactly. Great job, Caroline. Excellent work. I don't care. Another 50 points. Caroline, keep up the great work. And everyone else, keep up the great work. This is the practice we need. And memorizing this right here. Philanthropy, we'll do that one next after this one. I think came out 1, 2. One where he says probably arriving on time after 4 stops is probably arriving on time. I know that's wrong. We'll find it. We'll find it here. We are learning. We are just like concentrated learning right now. It's all Caroline, half out. Suppose the probability. I'm gonna try to read it over here. Suppose the probability of the bus arriving on time P for the next. Okay, so it's putting in the things right there. What's the probability the bus is on time for at least one of the stops? Okay. So this is a randomly generated probability right here. That's why it's got a placeholder. So we're going to put in a probability right here of 30%. Make my number nice. For the next n stops, we'll put in the next 4 stops. What is the probability? So yeah, we can do it right there. So suppose the probability of a bus arriving on time. So let's go here. Probability on time is equal to 30%. Probability off time, like not on time, it's either on time or not on time. That's a complement. So there we go. Does this make sense right here? You got it, Campbell. See, perfect timing, perfect timing. Yeah, let's do one next. You got it, Samson. And so we have here the probability on time is 30%. The probability off time is 70%. So in the next 4 stops, what is the probability that the bus is on time for at least one of the stops? Okay. Assume each stop is independent. So, okay, which is a major assumption. So why are we assuming things are independent of each other? Why are we assuming things are independent of each other? What rule are we going to be using? So this is a key thing. If you assume things are independent, you can use this rule. What rule are you using? We always try to slow it down, and we make sure we know why we're assuming independence. Like, that's a key word right here that we have to put in this problem. Which, is it really independent? Probably not. Adding is going to be disjoint, so we can multiply. Great job, Caitlin. Great job right there. And let me pull up 2 seconds, everybody here. I'm going to pull up the... Wait. I'm pulling up some stuff so we can take a look at this. Multiplication. And so 2 seconds. I have to finish up the thing for tonight also. Okay, so here we go. Oh, you can't see it yet. Okay. There. Oh, I just hit the extra credit button. There we go. Buttons that I rarely hit. Extra credit button. You know what? Watch this.
It's not the question you deserve. It's the one you need.
That button. I never hit that button. He's blocking me. Batman, you're blocking me, man. We need to use that button more often. Yep, so let's go down to that real quick down here. So here we are with the table that we should have in our notes. Please have this table. What does disjoint mean? So the first question here is, what is disjoint? Disjoint is one of the things we need to add things together. Think about two things that are disjoint. So who can name two things that are disjoint right here? This is in the asynchronous class, but you can take a screenshot of it or write it down right now. So it's the mathematics we're doing, the word that we use, and the rule that applies to it. So the multiplication rule uses the word and has the independence. It can be. And what does that mean, Grace? You are correct. Getting a dog or a cat can be disjoint if your parents say what. Getting a dog or a cat would be disjoint if your parents say what. Some parents, it might not be disjoint. You are correct. And I use that example a lot. And so, Ella, you are correct. And then that would, if they are disjoint, like your parents tell you, oh, you're going to get a dog or a cat, but these are going to be disjoint events. So you can only get a dog or a cat. You can only get one. So if someone gets a dog, they can't also get a cat. You might say, well, I can do that. And you're like, well, then they're not disjoint events. What about the Patriots winning the Super Bowl this year and the Patriots not winning? Well, now we got to talk about Tampa Bay, right? Because wherever Tom Brady goes. But when we talk about Tampa Bay winning the Super Bowl this year or Tampa Bay not winning the Super Bowl, are those disjoint events? Like this year, Tampa Bay will either win the Super Bowl or not win the Super Bowl next year. They'll either win the Super Bowl or not win the Super Bowl. Are those disjoint events? They will either win the Super Bowl or not win the Super Bowl. And they are complements. And are complements disjoint events? All complements are disjoint events. Because you can't win the Super Bowl and not win the Super Bowl. Does that make sense? Not both can happen exactly. That's what disjoint means, is that if one happens, the other cannot happen. Like if you win the Super Bowl, you can't also not win the Super Bowl. So complements are literally disjoint because this happens or this happens. They can't both happen. It's like A or not A. You can't have A and not A. Does that make sense? So what does independent mean? Independent means if you know one, it doesn't change the probability of the other. Ooh, Kayla right there with the mathematics on the empty set. That is correct. Nice job. A and B, when they are disjoint events, would be an empty set of possibilities. Yep. Nice job, Kayla, knowing the mathematics. So independent means that knowing A occurs just tells you nothing about B. So I always say things like, it's raining today. Does this influence the probability of my brother getting a promotion? So maybe my brother he's in for an interview and he has a 50% chance of getting a promotion and it's raining in Knoxville. So you might say 20% chance of rain in Knoxville, 50% probability my brother gets a promotion. These are the most independent things I can think of right now. Like my brother's boss is not going to be like, it's raining in Knoxville. We should really give Darren a promotion. No, these are completely independent. Knowing it's raining in Knoxville would not influence the probability of my brother getting a promotion. But when are things not independent? Well, what if we say it is 20 degrees outside today and the probability it snows? What would happen to the probability of snow, which might be 10% any day in January? What would happen to the probability of snow if it is 20 degrees outside? The probability of snow would do what? Now, you're not saying it will snow, but the probability of snow given it's 20 degrees would do what? Like if you know it's 20 degrees, so we'd say the probability of a temperature below 20 degrees is like 10% in Knoxville. The probability of snow is 10%. But now, what would happen to the probability of snow if it is 10 degrees outside? If it is, or 20 degrees outside? It would increase. So knowing that the temperature is low would increase the probability of snow, and that would be very not independent. So complements are disjoint. That is correct. Every complement is disjoint, and every complements are disjoint, and complements are either independent or dependent. So let's write this down, and then we'll finish the Canvas content. Complements are disjoint events that are they dependent or independent? Complements are disjoint events that are, yes, Ella, great work right there. Ella, excellent review. They're going to be, and we'll just delete this one. They're very dependent. Because if the Patriots don't win the Super Bowl, then they can't win the Super Bowl. Like, losing the Super Bowl depends on winning the Super Bowl. So if one happens, the other can't, it totally changes the probability. Complements are 100% dependent, because you could say, if your parents say you can only get a dog or a cat, then getting a dog would depend on getting a cat. Like, if you know someone got a cat, you know they didn't get a dog. It changes the probability of dog to 0. So you might say you have a 50-50 chance of cat or dog, and if someone gets a dog, the probability of cat is now 0. So good review of probability rules. I'm trying to remember like what we put in this video so I can mark it afterwards. Suppose the probability of the bus arriving on time is 30%. For the next 4 stops, what's the probability that the bus is on time for at least one of those stops? This is where it gets a little bit complicated, but let's talk about this right here. We have 4 stops in a row. 4 stops, which you really have to assume independence, which it's a little bit of an issue. But we're going to assume independence. It tells us to do that, so we'll do what the problem says. So would you agree with me? The bus will either be on time or be off time for 0 stops, or it'll be on time for 1 stop, on time for 2 stops, on time for 3 stops, on time for 4 stops. Does everyone agree with me? Like, you're watching this bus, it is, we're going to say it misses these, it's off time for 0. So let's see here. I'm just making sure I do this correctly. Like, I know the mathematics I got to do in my head, and just like I want to explain it properly. So exactly. Okay. So on time for at least 1 stop. Bingo. So it would be on time for 0 stops, on time for 1 stop, on time for 2 stops, or on time for 3 stops, or on time for 4 stops. What do you hear me saying? Ella, yep. Ella's got the answer. What are you hearing me saying as I say it's either on time for 0 stops, or 1 stop, or 2 stop, or 3 stop, or 4 stop? What do you hear me saying as I do that? I say it's either on time for 1 of the stops, or 2 of the, either 0 stop, 1 stop, or 2 stop, or 3 stop, or 4 stop. What am I saying right there? I'm using this or. Because when you talk about the probabilities of all these, they are all disjoint. Like, it can't be on time for 0 stops and also on time for 4 stops when we look at these stops. So we're saying, what did we observe? The bus was on time for all 4 stops. Cool. What are we actually interested in? We're actually interested in this right here. That it's on time for what? What are we interested in here? Who can put into words that the bus is what? The bus is what? They are all disjoint. You're exactly right. And look what we're about to do. We're interested in what? We're interested in that it's on time for what? So look up there at the top. We want to know that it's on time for what? Not at least 4. Just at least 1 of the stops. So you're on track right there. So we want to see that's on time for at least 1 of the stops. That's on time for at least 1 of the stops, which is what we have highlighted right here. So when you think about this, we're not interested. We are not interested. We'll use that nice color right there. We're not interested in this. Does that make sense to everybody? Like, that's the one we're not interested in. So this is everything that can occur. And so what is the probability of all this right here? If we think of everything that can occur, if we were to add all of these up right here, if you were to add all of these up right here, because they're all disjoint events, like it can't be on time for all the stops and on time for 0 of the stops. Like, it's either on time for 4 stops or 0 stops or 1 stop or 2 stop or 3 stops. If we were to add up all of these right here, the probability of everything added up would be what? The probability of everything added up right here. The probability of everything added up here would be what? 1. So all we need to do is just subtract this off from the other side. Does everyone understand? We're just going to mathematically take that probability right there. The probability is on time for 0 stops. And we're just going to subtract it off from this side. So what do we get right here? Here we can redraw this. Yay! Think it's going to work. Sure that works. Ooh, go down, go down, go down, go down, go down. A little more, a little more. You're almost there. There we go. And so did I do it this way? Did I do it properly? Oh my gosh, it's gonna work. Something actually works. And we're so close to making this drawing look great. Look at that. We're just gonna take and do 1 minus the probability of on time for 0 stops. So how did I get which one? Does this make sense, Campbell? We're going to do 1 minus the probability of being on time for 0 stops. So does this make sense? We're just subtracting it off. We're just taking, because it's added right here, we're just going to subtract from the other side, and then we'll get the probability it's on time for at least 1 stops, which is everything but it missed all the stops off time. Like this is probability of on time for 0 stops. So the probability of being on time for 0 stops is going to be related to this right here. So it needs to be off time for all the stops. Oh, so that won't equal 1. It'll be this right here is the set of everything that can occur. The bus will either be on time for 0 stops or 1 stop or 2 stop or 3 stops or 4 stops equals to one of those things must occur. Does that make sense right here, Campbell? Like the bus is either on time for 0 stops, 1 stop, 2 stop, or 3 stop, or 4 stops out of the 4 stops. Like one of these things must occur that'll be on time for 0 or 1 or 2 or 3 or 4 of the stops. And one of those things must occur. So, but if it's off time for 1 stop, then wouldn't it be off time for all the stops? Assuming, and this is a key assumption, I know exactly what you're saying. I do have a little bit of a qualm with this problem. I do agree 100%. We are assuming that each stop is independent. Caitlin, that is a very, very valid theoretical concern. And the problem tries to counteract that by saying, assume that each one is independent. But I totally agree with that, Caitlin. Valid objection, 50 points for valid objection right there. But the problem says, no, don't worry about that. It should say like random buses that are not not the same bus, because you are correct. It would influence each other. Totally valid concern right there. And so the probability of at least 1 is going to be 1 minus the probability of it being late for every stop. So it misses the first, it misses the second, it misses the third, and it misses the fourth. If you notice the key word right here, we're saying and. So we're saying it misses this, and it misses this, and it misses this. So here's the and right here. It's late, and it's late, and it's late. And we're just multiplying together the probability of being late. So the probability of being late multiplied together, and this would equal right here. So at least one of the stops is on time. Yep. So that would be everything but it doing what? This is everything but the bus doing what? So the probability of it being on time at least 1 time is everything but the bus doing what? Everything but. So here's everything, which is 1. Everything but, subtracting off, everything but the what 4 times. So the probability of the bus being on time at least once is everything but an instance where the bus is what? Everything but what? So what is 0.7? Mathematically, 0.7 is what up there? So everything but what 4 times? So this is the probability of it being on time at least once. Well, so 0.7 is not going to be the bus being on time. So, exactly. So everything but the bus being what? 4 times. Everything but the bus being off time 4 times. Like everything but the bus being off time 4 times. So it's all other instances, because this right here, I know this says 0 right here, but that is the bus is on time 0 times, which means it was what? If it's on time 0 times, like in 0 of the occurrence, it was on times, that means what? So this is maybe the confusing part. If it was on time 0 times, that means what for this down here? So it was on time 0 times. Yep, let me show the question. This is a tougher problem. And I do 2 of these. Has anyone watched the speed runs? Exactly, yep, it was off time 4 times. Has anyone watched the speed runs? I do two versions of this. These are some of the hardest problems. There's not a lot of these on the test, but these are the harder ones. And if you watch the speed run, I do 2 of them, and we did one during the Kahoot last night. So check that out. So this is an at least 1 problem, and it takes a little bit of practice. Check out the speed run if you haven't, but don't spend 3 hours trying to learn 1 problem. I wouldn't do that. There's a lot more to learn, and this is practice. And you just want to be able to, at least the more you can talk it out, the more you can graph it out and show your work. Like write it down. Yeah, no, Campbell, great question. These take practice. Like, and if you know, like Ella got it really quickly. And Ella, have you been practicing these? Because I bet you, if I write a problem right here, we'll do one more at least problem, then we'll do another type of problem. Like, let's see how quickly people can solve this. You ready? We're going to put the timer on the clock. So we're going to put the timer on the screen. Yeah, exactly, Campbell. Yep. So exactly what we're going to do right here. Let's do a speed run. Let's hop over and do a speed run of this. Oh, I brought up 2 timers now. Let me close out one of these. Okay, so we're going to do a speed run question here. I want to see how quickly you can solve it. So here we go. See how quickly you can get this. Put the answer in the chat when you get it, and then I'll do a quicker solve of it. That one was a long solve. We're going to do a quicker solve of this. See if you can get this quickly. Pause the video while doing this. See if you can get it. Don't spend 3 hours trying to learn this one type of problem. It's just one of the many, many types of problems that can be on the test. Okay, so here we go. Speedrun version of this question. Getting everything properly set up. Let's do this. You want to see the probability of at least one light bulb being broken in a 6-pack of light bulbs you buy. The box says that 98% of the light bulbs work. What is the probability that at least one of the 6 is broken in the pack? See if you can find it right now. I'm not going to solve it yet, but who can solve this right here? It's an at least one problem. Who can solve this out? Take a moment, see if you can get it, and let's see when the first solve is. If you practice these and you know the theory behind them, you can usually solve them like that. I'm hoping someone gets it in under a minute. I'm going to make sure I have it. So, yes. I think I have the answer. Reverse it, Ella. Reverse it, Ella. So you're on the right track, Ella. And that's usually what that can happen. You're right there. So I'm going to write down what you have and then always read it as a sentence. So I think you might be right. So let me see what you have. Everything but, and what is this right here? All what? I get it at 2, no, 0. Everything but what? So this answer right here is everything but what? So this is everything but all the light bulbs are broken. So this would be at least one is what? So this is everything but all the light bulbs are broken. So it's everything but all the light bulbs are broken. Every light bulb broken would be like this right here. All 6 light bulbs are broken. And we're saying everything but all 6 light bulbs are broken. So this is everything but all 6 light bulbs are broken. And this would be at least one is what? Because everything but all 6 light bulbs are broken. Like imagine an instance where all 6 light bulbs are broken. And now we're thinking everything but all 6 light bulbs are broken. Everything but the broken, at least one works. So this would be at least one light bulb works because everything but all the light bulbs are broken. So if we change this to the other way of doing it, which if we change the probability right here, this is everything but what? So now it's everything but, because mathematically, what is this right here? All what? So if you think about this mathematically, let's do some glowing light bulbs now. So this is, no, there we go. This is mathematically what I have highlighted now, just that portion, is all 6 light bulbs are working. So now it's all 6 light bulbs are working, and this is everything but all 6 light bulbs are working. So either all 6 light bulbs are working or at least one of the 6 is broken. Who thinks in this 3-minute quick solve problem where there's some light bulbs that went off right there where you're like, oh, I get it. Like, okay, everything but all the light bulbs are working would be at least one of the light bulbs is broken. And then always read it off and try to like graph it and these things right here. But this was a quicker solve of it. Hopefully, just I always want to try to explain things a different way. And we do it like the slow way or the quick solve way and be like, okay, what does this read off mathematically? Everything but, because one is everything, but is subtracting off. Everything but all 6 light bulbs are working. And so that's what that is. And just draw it out right here. And it's like, okay, this is the only thing we're not talking about. We're talking about every other instance, which is at least one is broken. So either they all work or at least one is broken. Do one more. Let's do one more. You got it. Okay. Yes, you got it. Now, Campbell, you got it. Ready? Speed run of this one. So be careful, and then always read it off. It's starting to make sense. We're going to do this right here. You ready? See, this is better than 3 hours. This is 3-minute speed runs. Let's do it. Here's another one right here. We buy lottery tickets, and we want to win something because reasons. The probability of winning something is 10%. What is the probability in 5 lottery tickets? There is at least one winner. So here is the problem. See if you can solve this out here really quickly. And what do you get? And then read it as a sentence to make sure you get it. Because, oh no, we didn't start the timer. There's the timer. Go ahead. Let's see. We buy lottery tickets and we want to win something because reasons. The probability of winning something is 10%. What is the probability that in 5 lottery tickets, there's at least one winner? So what is, just read what you have as a sentence afterwards, and then think about it theoretically. What do we have as the probability? What's the probability we win? There's at least one winner in the 5 tickets. That might be right. I don't know the answer numerically, but let me see what Ella has right here. I think Ella has it correctly. Oh, I'm sorry. Hair's getting way too long. So everyone check, because Ella's answer is correct. Does that solve to that, Ella? Double check Ella's answer, because Ella has the right answer right there, it looks like. So that looks like the right answer. And let's think about this. So what do we not want to see? If we want to win something, can anyone explain just, we don't want this. If we want to win something, we don't want to see this. Nice job right there. It looks like people have the answer. With under 1 minute, everyone's getting the answer now. It's like, oh, we're getting this down. What do we not want to see? If we want to win something, we don't want them to be what's. If we want to win something, just think theoretically about this. If you want to win something, you don't want to see this. If you want to win something, you don't want to see this. Anything but all losses. And literally, Jack, great job. 50 points right there. That's literally the mathematics right there. So Jack's already written out how to explain this. We don't want to see all losers. So what's the probability of winning? Probability of winning equals to 10%. The probability of losing is equal to 90%. And the probability of all losers is, well, that's the probability of losing one time. The probability of all losers is this. And we don't want to see all losers. We want to see anything but all losers. Because either they'll all be losers, like all 5 tickets will be losers, or what? Either all 5 tickets will be losers, or what? Exactly, I think Camel's on the right track. Either all 5 tickets will be losers, or at least one will be a winner. And if you notice, we're even faster now. We're doing it in just around 2 minutes there. So even faster solves we're getting now. So either all 5 are losers or at least one will be a winner. And always try to read this off as Jack did so perfectly right there. Jack said anything but, so that's anything right there. That's all possibilities. Anything but all 5 are losers. Anything but all losers, which is the mathematics right there. So the better you get at reading what you write down, like always read off what you have written down, because it's so easy to just choose the wrong probability and be like anything but all winners. Well, then that's at least one is a loser, because either they're all winners or there's at least one loser. And it's very easy to just change the mathematics to this. And if we change this 9 to the 1, now we have the probability of anything but all winners, which all winners would look like every ticket's a winner. So either they're all winners or there's at least one loser. And it's highly likely there'll be at least one loser, because this is a much different question now. So this would be probably at least one loser. So the probability of at least one loser is now on the screen. What's the probability of at least one loser? So it's anything but all winners. So if anything but all winners means at least one was a loser. So we changed the problem. We did 3 problems right there really quickly. What question is there now? What question do we have now to do? What question should we do now? As I'm just going to itch my eye and itch my contact. What questions are? Let's hop to the main screen. It is your time to ask questions. Great questions. Really great review right now. Did 3 at least one problem super quick. I think a Canvas. Someone wanted a my Pearson problem. And thank you everyone who comes to office hours. I think the questions, like, office hours get viewed by a lot of people. I am in shock that some of the videos nearly have 1,000. Some of them do get 1,000 views, which just blows my mind to think that office hours would get 1,000 views. Like, that is insanity. Probability of boy and girl from content quiz. You got it. Let's go grab the content quiz question. Thank you so much. And I'm sure the people who are taking these are very thankful that the questions are being explained and talked through. So, where is that question? I saw it earlier. Really? Really? Where'd the question go? I'm losing my mind. Here we go. Here we go. Is it Jim and Carly are planning on what is the sample space? Okay, cool. What is the sample space? I might actually have to like cancel. Okay, here we go. I generated this one a moment ago. Okay, 2 seconds. I'm gonna try to generate it again. Okay, give me a second here. I think it wants the sample space. So here we'll do a sample space type question. Let me do a sample space. So this is, let me look at the question again. I'll make sure I'm doing an exact version of it. Yeah, okay. Okay, so we talk about the sample space right here. Sample space, not sample frame. Ah, yes. So the difference between the sample space is everything that can occur, and the sample space, the sample frame, is what we're sampling from. An event tomorrow takes the 15% minutes, and the complement would be the event take. Yes. Less than 15 minutes, 15 minutes or more. Exactly, Cooper. Great answer there, Cooper. Just to clarify, this is kind of yes or no, but when doing the sample frame, do you include all orders if it can happen or just the possibilities? It'd be all orders. Yep. So let's say you're buying 3 lottery tickets, and so your lottery tickets can be winners or losers, right? So does everyone agree when you buy lottery tickets, your lottery tickets can be winners or losers? What is the sample space? And this is everything that can occur. So let's write here a definition. Sample space, everything that can occur, includes order of occurrences. So when you think about the sample space right here of lottery tickets, let's just do 2 lottery tickets. That's the easiest way of doing this. What is something that could occur when you buy 2 lottery tickets? So lottery tickets are winners or losers. And what is something that can occur when you buy 2 lottery tickets? Just give me anything that could occur. You buy 2 lottery tickets. Tell me what happened. What happened to you with W and L? And this will be the answer to the other question too. Ella's like, boom. Caitlin won both, and Ella's got the sample space. So you could win twice. You could win, lose. You could lose, win. You could lose, lose. And this is what a sample space looks like. When we talk about the sample space is equal to these things right here, this is everything that could occur. Now with 3 lottery tickets, it's going to get more complicated because there's a lot more things that could occur. Amazing job, everybody. And we just have to permutate through on this. There we go. And then there we go. And then this needs to have 2 losses now. So, and oh, we almost got it. It's almost going to be on the screen completely. I think we've done it here. Oh, so here's the sample space of 2. Here's the sample space of 3 because you could win on the first 3. Yeah, let's do the casino one. You got it, Jessica. Thank you so much. We go right here, and these are the things that could occur. Does this make sense to everybody? Like, these are all the things that could occur. You could win on 3 of them. You could win on 2 of them. You could win on 1 of them. You could win on none of them. And so all these right here are the different occurrences with 3. WWL. So these are what sample spaces are. Sample space is everything that can occur, includes the order of occurrences. Does everyone feel good about what a sample space is and the definition of a sample space? It's saying, like, you buy lottery tickets. This is the sample space of 2 lottery tickets. This is the sample space of 3 lottery tickets. It's everything that could occur when you buy 2 lottery tickets with winning and losing. So you could win twice. You could win 1 time. You could win none times, 0 times. With 3 lottery tickets, you have 3 wins, 2 wins, 1 wins. And these all right here are disjoint events. And we could also talk about the probability of winning like a certain amount of times, like 3 wins, 2 wins, 1 win or 0 wins. And then you could find the probability of losing or losing at least once. Or you could find the probability of winning at least once. So we could actually do the same sort of stuff we were doing before, where we figure out the probability of winning at least once, because all of these are disjoint events. So the sum of the sample space equals to 1. Very similar to what we were doing before. Let's head back over and do that other question about the lottery stuff. So great questions, everybody. We got 19 more minutes. Let's do this. Let's do this. I'll grab some food between this. We got this. Let's look at the lottery question. Here we go. You are at... Okay. You're at the world famous Law of Large Numbers Casino. It's probably a good thing. It sounds like they use mathematics. Okay, so here's the question. Let's make sure everything's on the screen properly. I need a resize button that does that. I could do that. So you are heading to the Law of Large Numbers Casino for spring break and plan to play the world famous slot machine. The slot machine at the Law of Large Numbers Casino has 3 wheels that spin when you pull the lever. When pulled, each wheel spins and stops on a symbol. Assume that each outcome is independent. What are we doing? By assuming independence, we now know we can what probabilities together. By assuming independence, we're probably going to use what through this? By assuming independence, what are we able to do right here? By assuming independence, we can multiply. Nice job right there, Kaylin. Excellent work. Yep. That is the rule for independence, or that's the rule for multiplication, is we need to have independent events. So make sure to have this down. Great job, Jessica. Yes, we need to assume independence to multiply, or no, it's independent. So questions will usually state this, especially when they're using the multiplication rule. Great job right there, Hannah. Each wheel has 10 equally likely spaces. Good. That means we can just say the probability of a skull is 40%. The probability of a lemon is 30% because they're all equally likely. The probability of a cherry is 20%. And the probability of a bell is 10%. If you play, what's the probability that you get a lemon, cherry, and bell? And it's talking about in that order. Like, this might seem more complicated because if you go through permutations, we're saying the first is a lemon. And then you get a cherry. Got to make sure to use the right probabilities. And then you get a bell. So I think this should be it. I think we just solved the problem. I was like, I don't want to solve it. And I was like, I don't want to solve it. So the probability of a lemon, cherry, and then bell. And it's not talking about in like a different order. It's saying you get a lemon, and then you get a cherry, and then you get a bell. So the key word right here we should notice is and. So it's not, I like for it to always be there, but it could say like, what's the probability you get this, you get a this, then this, then this. But the and really helps. If we see and, we're just multiplying the probabilities of lemon and then cherry and then bell. And then we just take those associated probabilities and multiply them together. And this is the likelihood of that specific sequence, not of getting them in any random order. So it should be 0.006. Let me look at that answer. I'm always afraid I'm going to get it wrong. And then everyone will be like, Brian. I'll be like, I'm sorry. Sometimes my brain malfunctions. Yes. There we go. 0.006. Right answer. 0.006. Not saying that's the answer, but not saying. What other questions are there? Chase, good to see you here. What other questions are there? Is my Pearson working properly now? My Pearson, why do you do this to us, my Pearson? My Pearson looks to be working. I think there was a chapter 13. My Pearson looks to be working. Sorry, everyone. This morning it was weird. Or maybe it's still weird now. No. What questions are there? It's your time to ask questions. Any questions you have, let me know. What questions are there? What questions are there? We could review the formula sheet. So who would like the formula sheet to be reviewed to end office hours? Might be a good end of office hours to be like, let's bring up the formula sheet. If people want to do that, we can. I'm assuming right now, unless you're free to ask any question you want, and I'm assuming the formula sheet's going to be like, yes, formula sheet, but it could be like, no, don't do formula sheet. No one's responding. Sounds lovely. Thank you, Caroline. Thank you, Caroline. So let's go grab the formula sheet right here. I agree. It does sound lovely to do the formula sheet. Okay. Let's talk about the formula sheet to end office hours. So, and thank you, everyone. Can you do number 6 on the practice exam? Yeah, let's do that real quick right here. Let's go to number 6 on the practice exam. So, and then we will do formula sheet afterwards. So, practice exam. And did you know there is a playlist? So, let me pull up this playlist right here. A lot of people don't know about all the playlists we have. There's a playlist where I go through and I explain each problem. Do not worry, though. I'm not being like, go check out this playlist. I mean, I am saying that, but I will also work the problem here and explain it. Is that called Test 2 playlist? Where is it at? Too many playlists, Brian. Why'd you do this to us? It's on the, let's do that. You know what the easiest thing to do is if you go to the page right here and you scroll down the Quizlet, and it should give you access to the Quizlet. I just accepted some people last night. There are practice review questions right here, and all the questions right here should be go over. So it looks like this might be the sampling distribution question. So each of these are gone over right here. So I go through and I explain kind of how to do each of these problems. Is this the one you're looking for right here, the sampling distribution question for number 6? And I go through the water heater problem right here, which we can do this right here. Does that make sense, Chase? And definitely check these out, but please ask questions when you have them. Please be like, hey, Brian, can you explain the inner workings of this problem right here? But in these videos right here, I animate them and talk through them and explain the problems. And so, perfect. Do you want me to still do it, Chase, right here and explain some of the inner workings of it? I just don't want to be like, check out the playlist. Go watch the video. That's not what we do here. We explain the answers. Number 6 right here. So let's talk over a little bit about number 6. The key to number 6 is going to be notation, 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 notation. So the key to number 6 is going to be notation. So check out those playlists. They're on the channel. Those are really good playlists. So we put them on the Stat1 webpage to make it easier to find, because even I have trouble navigating the playlist sometimes. Okay. The owner of a new apartment complex must install 50 water heaters. Let's say that the proportion of all always hot brand water heaters will last 10 or more years is this. So that's assuming this is true. We can think about these 50 water heaters that they want to own as a random sample. Ooh, sounds like a condition right there from the always hot water heater brands. After 10 years, by the owners, the proportion of yada, 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 that actually lasts 10 years. The proportion can be thought of as a sample proportion. Okay. So when you're doing this right here, they don't know what will happen in the future. But this company advertises that the true proportion of always hot water heaters that will last 10 years is this. So what does this make this number right here? What is 0.25? Because this is what they're saying is true from the company website. They're saying this is true, that after 10 years, 25% of your heaters will work. So they're saying this is true. They're saying this is the truth. So that's a key thing I'm trying to tell you right there by saying this is the true proportion. So what is that in notation? They're saying this is the true proportion of water heaters that will last 10 years. Exactly, Ella P. Great job. That is P, and we're going to take a sample of 50. And think about this. We are wondering what will happen. Does this make sense theoretically right here? Like, we're wondering what will happen in a sample, Grace. Like, we know, so apparently we know that 25% of these water heaters last 10 years. But then we're saying, what will happen in this sample of 50? Now, if we meet the sampling distribution of the sample proportion, we can actually talk about the sampling distribution of all possible proportions for sample size 50. That is correct. So we're saying what will happen in a sample of 50? Do you think it's possible? I just want to hear, no, don't think probable. Is it possible that all of our water heaters will work after 10 years? So we're buying 50 water heaters. Is it possible all the water heaters will work after 10 years? We can actually figure it out mathematically another way. The probability that they all work after 10 years is going to be this. This is the probability that every water heater works after 10 years. That's very unlikely. I mean, it's possible, but that's the probability that all water heaters will work after 10 years is 0.25, because the first one works and the second one works and the third one works. So looking at this right here, and this is kind of a quicker version of this problem. When you think about this, what proportion of water heaters would you expect? Like if we say, I would expect on average for the sample to see this. What would you expect in a sample of 50 water heaters? What proportion of them would you expect to work? Like after 10 years, what proportion of them would you expect to work? Not saying this is the amount that will work, but what proportion of them would you expect to work? What proportion of the always hot water heaters would you expect to work? So this is saying, I would expect to see like on average this many. Yep. And that is P right there. So we would expect to see on average 25%. And then we need to find the variation, because we're not saying 25% will work, but we need to find the variation, which is going to be P times Q over N square root. I want to rewatch the video because I don't think I started saying that about 5-6 years ago. When did I make those videos? I don't know. Oh, it's all blur. There's P times Q. Q is the complement of P, so it's just the other side of it. And then we do over N, and we square root it. So let's go ahead and solve this. P times Q over N square root. That is the biggest calculator I've ever seen. So P times Q over N square root. So about 6%. About 6%. And so 0.061. And that right there is the standard deviation. And what we need to do then is we need to go and draw the distribution. Now, if we meet all the conditions, which this question goes over too, the distribution will look what is the point? This is mentioned at the start of this office hours. What is the point of meeting that they are randomly selected, they're less than 10% of all water heaters, and we have at least 10 successes and at least 10 expected failures, which we do meet for this. Because if we have 50 water heaters, we'd expect 25% to work, meets 10 successes, 10 failures. If we have 50 water heaters, we would expect 75% to not work. It'd be normally distributed. So by meeting the randomly select these water heaters, 10%, they're less than 10% of all water heaters, which, assuming they make more than 500, this is less than 10% of all the water heaters that this probably large company makes. And then last but not least, we have a success failure, which means we need at least 10 successes, at least 10 failures, found by NP and Q being greater than or equal to 10, and sub in your numbers right here where we have NP or P and Q and N. Sub those into this formula, and you will find that they're each greater than or equal to 10. We just solved them out mathematically, and they were 12.5 and 37.5. NP was 12.5, and NQ was 37.5. So when you solve all this, you'll get, and this is just a abbreviating the numbers. Well, we can do this right here. There we go, and 0.37. Oh gosh, I hate that it does. I hate that it does that. It brings the cursor back to where it's at. So when you do this, you're just going up standard deviations, because the standard deviation was P times Q over N square root. And so we just take the mean and we go up and down the standard deviation. So these are the numbers right here I'm using, and then I'm just going to go up another standard deviation, and those are the numbers I'm writing on this curve. And then we could see above 37% is where it would be unusual. So this is the idea of an unusually high occurrence beyond here, or an unusually low occurrence below here. And yeah, a little bit of a quicker solve right there. We're going to do the formula sheet because I'll be teaching here in 26 minutes. I'm going to try to grab some food between all this. But let's go check out that formula sheet and talk through it right here. So this is a talk through the formula sheet, and I might put this as a standalone video. So with the formula sheet, let me head over to the speedrun screen. Let's speedrun the formula sheet. Okay. Here we go with the formula sheet. Let's do this. So on the formula sheet right here, what is the first thing? The probability for the set of all events that are occurring. So we have here the probability of the set of all events. And word is breaking. So the probability of the set of all events is going to be equal to 1. So this is just anything that could occur. If you think about like a football game, if you talk about the probability that people can win, lose, or tie in a football game, that is going to be the set of all events. This is the empty set right here. So we really don't use this one much in our class, but the empty set right here has a probability of 0. It's just everything that can't occur. So this is the empty set. We really don't use that much. Next, and Microsoft Word is just not working right now. What am I doing? I'm going to reset this. Really? Oh, now it's going to work. Hey, it's working now. We got it. Okay, good. Don't know what I was doing. So now we have next the probability of the complement. So either something occurs or the complement occurs. So we have right here that you either, let's say, make an A in the class or you do not make an A. And if the probability of making an A is like 40%, the probability of not making an A is 60%, because you either make an A or not make an A. So the probability of A is 40%. The probability of not making an A is going to be 60%. And you can see right here, they both level out there. So something plus its complement is equal to 1. Let's write that out right here. So the probability of 1 is equal to the probability of A plus the probability of not A. So this is what we're doing right here, is we're just doing this multiple ways right here, that something plus its complement is equal to 1. So we have the probability of A or not A right here, and that is equal to 1. So the probability of A or not A, and we can solve it out a few different ways right there. Next, we have the multiplication rule and the addition rule. First, the addition rule, and things must be mutually exclusive or disjoint. Mutually exclusive and disjoint are the same word. It just means that things do not have overlap. These two things right here, A and B, cannot occur at the same time. They are mutually exclusive, but this right here would not meet mutually exclusive because they have an overlap right there. So when you see that two events can occur, like if you can get a dog and a cat, these would not be disjoint events because they can both occur. There's an instance where A and B both occur, and that is not mutually exclusive or disjoint. The same word to say disjoint, mutually exclusive means the same thing. Now, independent means something different, and if we meet the rule of independence, we can multiply things together. So if you're multiplying things together, you need to make sure they're independent. And independent means if you know A, it tells you nothing about B. So when we know A, we know nothing about B. Like, it's raining outside today, and Brian's brother gets a promotion. Knowing it's raining, event A, tells you nothing about Brian's brother getting a promotion. If the rain has a probability of 10% and Brian's brother has a probability of promotion of 50% today because he's got an interview or something like that, or I guess a review, then the probability of it raining and my brother getting a promotion would thus be 0.1 times 0.5, so it would be 0.05, the probability of both occurring. Next, we see the sampling distribution, which we've done lots of problems on, but let's read this. When we're doing the sampling distribution of the sample proportion, the mean for the distribution, which is what we expect. So let's do some drawings right here. The mean, which is what we expect. This is the mean right here of the sampling distribution of the sample proportion is equal to P. And what does this mean? Well, if I tell you that 70% of UT students are in state, and you went out and sampled, you would expect to see 70% of in-state students in your sample. Because I just told you 70% of students are in-state, so you would expect to see in a sample 70%. Like you go out and talk to 100 students, you'd expect 70% of them to be in-state. You go out and talk to 200 students, you'd expect 70% of them to be in-state. The sample size doesn't matter here. It's just if 70% are in-state, and I'm stating that as a truth, that 70% of students are in-state, well then the mean of the distribution, which this is the mean of the distribution right here, is what you would expect to see when you take a sample. So we see right here the mean of the distribution is the center, and that's what we would expect to see, and we'd expect to see the truth. What does the other one represent? The standard deviation. The standard deviation is just going to be the variation we see, and it's going to go up by 3 standard deviations. There's further out than 3, but 3 is where we would pretty much say it's very, very unusual if it's beyond 3. 2 is kind of unusual, 2 is a little bit high, and 3 is very, very high. So the more standard deviations we are away, the more unusual it is. And this tells us, the standard deviation tells us how unusual something is. Now, a really great thing to use is the formula right here. The following formula gives us a z-score. The z-score is going to give us how many standard deviations in context. So we can actually figure out via this formula right here, the z-score, and find out in context if it's unusual. So anytime something says, find the z-score, or is this unusual in context, we can use that right there. So that will solve for the z-score, which is going to turn it into how many standard deviations above or below the mean. When you look at this formula, we're just taking our sample proportion right here, which is what we observe. Like we observe something like a sample proportion here, and that would be your sample proportion there. We subtract off of it the mean, and the mean is going to be the center of the curve. So let's re-highlight the mean right here. It's in yellow. So there's the mean, and then the standard deviation is going to be how many standard deviations above or below it is. So we're just saying the observation minus the mean of the distribution over the standard deviation, and that's what a z-score is. Observation minus mean over standard deviation. We are standardizing this distance that it is away in terms of standard deviations. Last but not least, we have the confidence interval formula down here. And let's point out some important stuff about this confidence interval formula. When it comes to this confidence interval formula, we have starting here p hat, which is the sample proportion. So p hat is found via x over n, where x is the number of successes and n is the sample size. This is like saying I go out and I talk to 200 students, and in 200 students, 50 of them own a dog. So the sample proportion of students that own a dog is this. Now this differs from the true proportion because it has a sample size. All sample proportions will be relative to a sample size. So the sample proportion of my 200 students that own dogs is 25%. So it's relative to a sample size. So we know that p hat is the sample proportion, and it must always have a sample size associated with it. After the plus or minus, everything we're dealing with from here on out is a margin of error. So this is the margin of error right here for the equation because it has a plus or minus. The z-score gives us the percent confidence right here. So when we make a confidence interval, we can be a certain amount of confidence based on the percent of the curve we cover. So if we want to go 95% confident, which we would give on the test, we would give a z-score like 1.96, and that would be given to you on the test for 95% confident. But if we wanted to go up to a z-score of, let's say, something like a z-score here for a 99% confidence, that would be 2.5758. And if you notice, the more confident you are, the bigger the z-score is, because it's going to cover more and more area on this curve. So more and more area on this curve would be covered as we go more and more confident. The z-score is going to be for the percent confidence on the curve. Last but not least, we have the standard error on the curve, which is going to be p hat q hat over n square root. And we should mention what q and q hat are. They're just the complement of p hat. So whenever you're solving for q hat, remember that p hat and q hat add up to 1. So I always like to play the p hat and q hat game. If p hat were to be something like 0.8, then q hat would be, that's a horrible q hat, we'll keep it, I'll delete it. Q hat would be 0.2. Always try to solve these before I say them. So what if p hat was like in our previous problem, 0.25, excuse me. The answer to the next one, and you can't see it on the screen right there, hopefully that last one showed up. If p hat was 0.25, then q hat is 0.75. So p hat and q hat are always complements of each other. Complements mean that they add up to 1, and that's a review of another probability problem. Solving all of this right here is going to give us the standard error, which is basically like a standard deviation, but comes from a sample, and it's just a measure of uncertainty. And solving us gives us the confidence interval. Great job, Robert, and everybody. That's a review of the whole formula sheet, and we got it. Good luck on the test. Woo! Good office hours, everyone. How's everyone doing? Let's put on some music right here. I need to put back on the system audio. How's everyone doing? Woo! Class here in 17 minutes. Chase and everyone, good to see you. Whew. Busy office hours. Test coming up. News for 320. We've got some good news for 320 about assignments and about homework. We're working on some stuff with Terry. So 320, Roderick and everyone. Good news with assignments and homeworks. Big announcements to come. Woo! Great office hours, great review. Is there any reason to get 10K points? You just keep going prestige levels. Higher and higher prestige levels. Let's throw out some 50 points right now. Higher and higher levels. This is prestige mode you're in right now, but keep getting points. Keep trying to get more points. You get higher and higher levels. The rewards get smaller, but there are more levels. We have some people at some really crazy high levels. It's really fun to see this semester, like all the points. So keep getting more points. With that, you're welcome, Tori. Great job. All the points, Caitlin says. All the points. You know what? Left 50 points. So the rewards are, it's in your name. You'll notice when you type your points, you can see like you have 2.1 points or 2.0 points. Like Caitlin right there at 22,000 points has 2.111 points on their grade. The ones keep going for a while. If someone maxes out, it'll be insanity to see someone get to, because there's higher and higher levels. So there's some ridiculously high levels. So keep going for those higher levels. So you're welcome, Caitlin. Keep going for those levels. It's fun to watch, and like people get super excited when they get to the next level. It's harder. It's like Pokemon Go, where each level gets harder to get to. But the amount of points you get levels off. You can't get to like 3-4 points in the class. You can't like ace the class by getting bonus points. But there's this leveling off where it goes 1, 1, 1, 1, 1. The point value decreases. But keep it up. With that, I'll be teaching her in a little bit. I'll see you in class, or I'll see you in the next office hours. Bye for now, everyone. Bye!